Okay, this is a continuation of section 2.5 for MAC 1105. We've been discussing various transformations, the vertical shifting, horizontal shifting. We've also gone over reflections when a parent graph will flip over the x-axis. That's called reflecting about the x-axis, and when it will reflect over the y-axis. And now we are moving on to stretching and shrinking of graphs both vertically and horizontally. Those will be the next two things that are presented. So when we are talking about a function that has vertically stretched or vertically shrunk, you can see pictures of the following. First of all, the placement of the multiplier. It is a multiplier that's going to be present in the function, and you see that they have the C right out front here. This is the way that you know it's vertical shrinking or stretching is that the y-coordinate is acted upon by a multiplier. Now that multiplier can either be greater than 1 or it can be some fraction in between 0 and 1. If it is a number greater than 1, then what's going to happen is that the graph is going to be stretched vertically up and down, vertical stretching. So it'll be pulled both up and down, kind of narrowing out the graph. And if the multiplier is some fraction between 0 and 1, then it will vertically shrink. It will come in this way. And you can see the diagrams here. The blue graph is the original. Reddish line is the line where it has been stretched, pulled up and down, stretched vertically. Again, the blue graph in this one for a vertical shrinking is the blue line, and then this reddish line is the vertical shrinking. So now we're going to try this on an actual problem, trying to be able to read the commands. Again, you can kind of tell from you can very well tell what you're supposed to be acting upon based on where the C value is placed, because sometimes you're going to see that in the next examples that multiplier is right in here with the x. That means act upon the x values using the C. But when it's out here, this says take the f of x values, which is really y, and act upon them using the multiplier. Okay, so like for instance, let's say that you are given the following problem. We're going to examine the impact of the multiplier on the parent graph. It's easiest to see what the impact that it has had on the graph just by putting the parent graph and the transformed graph both on the same set of axes. So parent graph, I'm suggesting 4 points. All of these come from the absolute value graph. I simply selected -2, 0, and 2. I plugged them right in here. When I plugged in -2, absolute value was 2. When I plugged in 0, absolute value was 0. When I plugged in 2, absolute value was 2. So very easy to plug in basic values into the parent graph. And then instead of continuing to plug into the functions, we can just work off of these points if we understand the commands that are being set forth to us and the transformations that they suggest. So for instance, this is the function f of x, and you're being told to multiply by a 4. Notice that this 4 is not up inside of these grouping symbols, the symbol that gives it the shape. The 4 is not inside there. So you're not being told to act upon x, you're being told to act upon y. If they wanted you to act upon the x, it would be inside here. So we're going to be multiplying those y coordinates by the 4. 4 is used as a multiplier on the y coordinates. So transformed points will now look like this. Let's get 3 points based off of the 3 points in the paragraph. Remember, we're affecting the y coordinates through the multiplier, so I would just concentrate on doing that first. Okay, so let's see. The y coordinates are 2 multiplied by 4. That would be 8. 0 multiplied by 4 would be 0, and 2 multiplied by 4 would be 8. You have not been told to do anything to the x, so those remain as is. -2, 0, and 2. We now have points for the original graph, and we know the shape caused by absolute value, as well as the transformed points, where we have multiplied by a value. Now remember what was said up here, that if the C value, the multiplier, is greater than 1, which ours is, it's a 4, we can expect vertical stretching where it's stretched up and down. And you'll see the appearance that that gives as we go and graph these points. Okay, so we already know that it is vertical stretching. We have to choose that, and then you'll see that in the graph. You can look at the graph first, of course, and then choose that. So negative 2, 2 would be right here. 0, 0 would be right here. 2, 2 would be right here. Make sure to give it the absolute value V shape and not the parabolic shape. Get familiar with the shapes of the graphs. Then we've already performed the transformations on these original points rather than plugging into that repeatedly with whatever x values we were using. So just some simple operations got us negative 2, 8, 0, 0, and 2, 8. So let's plot those. So let's see. We're going to go to negative 1, negative 2, but we're going to shoot all the way up to 2, 3, 4, 5, 6, 7, 8. And you see that this is taking on because it's being stretched vertically. It's taking on a much narrower look, which you'll see when I complete the graph. The other points are 0, 0, and 2, 8. These 3 points with the same shape that you've connected the original points. Notice that it has taken on a much narrower appearance because it has been vertically stretched upward. And so that is called vertical stretching. That happens whenever the multiplier on the y values is greater than 1. Moving to the next page. We have what's called horizontal stretching and shrinking. A function that stretches or shrinks horizontally has a multiplier that impacts the x value or the x coordinates. Notice that the C is a multiplier that is on the inside of the parentheses this time. That multiplier is right up inside of there with the x, likewise on this picture. Now there are 2 different kinds of horizontal transformations that can occur. You can have a horizontal stretch or you can have a horizontal shrink. When it is horizontally shrinking, that's because the C value that's inside here with the x is going to be greater than 1. It will be presented as a value greater than 1. And I'm going to make some points about why it is shrinking when the value is greater than 1. And to some students think, well, if it's bigger than it was typically, it should be stretching. But I'm going to make some comments that might help you to make more sense out of that. When the C value that's presented in the transformation is between 0 and 1, some fraction between 0 and 1, it will actually stretch the graph horizontally. Again, I'm going to point that out. I'll point out why. Note that when the multiplier is greater, when the graph shrinks horizontally, the graph actually gets narrower. And the graph stretches horizontally when the value is some fraction between 0 and 1. It gets wider. Horizontal transformations, and I tried to really make a point of this, are performed opposite to the operation presented. So let's say that they give you something like this. Look at the operations that are being presented so that you can possibly understand this and understand why what you think is going to happen, the stretching and the shrinking, is kind of the opposite of, what comes to mind when you look at the original numbers that are in the equation, like parent graph with 1x squared. Here is a parent graph that has a horizontal transformation that's about to happen, and if you know how to act upon it properly, then you'll understand why this fraction, a number between 0 and 1, why that is really going to cause a stretching rather than a shrinking, as you might think, by the 1/2. If this is true, that horizontal transformations are performed opposite to the operation presented, look at the operation that's being presented. You're being asked here to multiply x by 1/2, to literally cut it in half. What would be the opposite of cutting something in half? Doubling it or multiplying it by 2. So note that the multiplier can be read x divided by 2. So the opposite operation would be multiplication by 2. Okay, be very clear about that. So when you thought possibly because you saw a 1/2 as a multiplier that things were going to shrink, in all actuality what's going to happen is that they're going to stretch, and that's because you are performing the opposite operation. Rather than cutting the x values in half, you're going to be doubling them. So hopefully that helps you to understand why when you really start off with a fraction between 0 and 1, you're really going to stretch. You're going to stretch this graph by performing that operation only because you must perform the opposite operation. So looking at the points that I've suggested on the parent graph, again, I got these points just by picking whatever I wanted for x. I chose some small numbers. I chose -2 and its positive counterpart over here because it just makes the calculations easier, because when you do this calculation, you're really doing both of them. And I also chose a number in between, an x value in between -2 and 2, which was this 0. And I just plugged each one in one at a time. -2 right in there, squared would be -2 times -2, or 4. Whether you put a -2 in here and square it, or whether you put a +2 in here and square it, squaring always results in a positive number because you're multiplying a number and its sign by the same. Everything has to be exactly the same in the two things that you're multiplying. So that's why they both came out to be +4. When you put a 0 in there, it comes out to be 0. So now we have how we got these 3 points on the parent graph, transformed graph. Let's get our 3 points right off of these 3 points, and understanding that if in the transformed equation it says to cut the x values in half, you are really going to be multiplying the x values. You're just going to multiply by 2. That's the opposite operation of cutting in half. So we're going to take those x values and multiply by 2. So -2 times 2, -4. 0 times 2, 0. 2 times 2, 4. We have not been told to do anything to the y values, so we'll take the y values that were presented in the original graph and copy those right into these points. And we've carried out the transformation on x that we needed to. So let's see, does the transformed graph exhibit horizontal stretching or shrinking? We've discussed why those x values have just caused stretching to occur, but you'll also be able to witness that right in the graph if you want to wait until after you've graphed both graphs, parent and transformed graph, in order to answer that question. You can wait on that if you want to. So the original points, let's keep in mind, we should be making parabolic shapes as we connect these points. So one point is -2, 4, 1, 2, 3, 4, right up there. One of the points is 0, 0. One of the points is 2, 4. I am plotting those points right now. Connecting them with a parabolic shape. Okay, then plotting the transformed points, which we have predicted are going to horizontally stretch that parent graph. So now we have -4, 4. That's -1, 2, 3, 1, 2, 3, 4, and we're going up to 4. So 1, 2, 3, 4 right there. And then we're also going to plot 0, 0, which we already have. Then we're also going to plot 4, 0. Supposed to be a 4. We're supposed to copy the y's just as is. This was supposed to be a 4. Let me correct that. So that was supposed to be 4, 4. Just caught myself doing that. So 1, 2, 3, 4, and up 1, 2, 3, 4. And then look at what this new graph does. See how it stretches out horizontally? The width of the graph is now even wider than it was before. So this is your g of x graph. This is your f of x graph, and we have just demonstrated horizontal stretching. Okay, moving to the last page of the outline. We have some information on what order should